All right, hello and welcome to a presentation on digital twins in the field of wind energy, emerging technology and industry-informed future directions. This is based on an IEEE Access journal paper, and this has been a paper which is done in collaboration with major industry players in this particular space in the Norwegian market. And I'm just trying to provide a bit of a succinct summary of what's been discussed in the paper and what we can take away from this particular paper in the field of digital twins. So let's go through what I'll be covering today. I'll be covering a bit of an introduction into what the paper tries to talk about. We'll then go into the concept of digital twins and the technology levels or the sort of standards around digital twins, like the different types. We will look at the various industrial players in the Norway market. We'll cover some challenges that have been faced, and we'll also go through the solutions. So let me start off with an introduction to what this is all about. So the paper talks about how wind energy is going to play a very important role in limiting global warming. So as you know, obviously we've right now got all these different sustainable energy sources which are trying to take over from fossil fuels. And wind energy is one of the fastest growing energy sources globally, with a 53% year-on-year increase since 2020. And the EU wants to achieve a climate neutral status by 2050. And for that goal, wind energy is estimated to form 56% of the power production in 2050. And we also want to have 26% of our power production coming from wind energy by 2030. So looking at all this, the worldwide energy electricity generation capacity for wind is estimated to grow by a factor of 8 until 2050. So this is a really high growth industry. And in order to sustain the growth, we want to reduce the cost and environmental footprint of the wind energy. Now, the thing is, if we reduce the cost of the wind energy, along with a lot of increase in turbine size and all that, we will not have further benefits without more new innovations. Basically, we can't just indefinitely keep reducing the costs and increasing like the size of the wind turbines and stuff and expect things to get cheaper. So what we need to do is increase the efficiency of the wind turbines. If there was even a worldwide 1% increase in the overall energy produced by the turbines, that would result in more than 30 terawatt hours of additional electricity every year, which is roughly similar to adding an extra 3,600 wind turbines for free, an extra $1 billion in revenue annually for the owners of wind farms. And essentially what we're saying here is, rather than trying to make things more and more cheap, let's try and increase the efficiency of what we already have. Okay, and the thing here is digitalization can be a really good tool in sort of bringing about this extra 1% increase in efficiency. About 30 to 34% of the levelized cost of electricity in wind power, or the real cost, is estimated to stem from operations and maintenance, and we're not even talking about catastrophic operation and maintenance. So the operation and maintenance cost can increase by up to 95% of the investment cost. So it's not just about building the wind energy farms, it's about maintaining it. Okay, and the maintenance cost can be really high. So the thing is, these wind farms are also located in areas which are remote and hazardous, and if we can maintain it autonomously, it reduces the number of maintenance jobs on the site, and predictive maintenance will go a long way in eliminating unexpected downtime and preventing catastrophic failures by taking action before small faults get out of hand, right? So looking at all this, digital twins are basically the solution, okay, to our issue of predictive maintenance, and that is what this study is going to look at. It's a very underutilized concept, especially in this wind energy sphere, although it has been highly used in other areas. But this paper is essentially going to take a look at the ways in which the industry currently uses digital twins, and essentially, sort of see what the current challenges are, what we could focus on for further research, and what the business opportunities, etc., and just an overall look at the state of the art in digital twins in the field of wind energy. So the first thing we need to do is take a few definitions of the digital twin. Okay, so let's have a look at the digital twin, digital sibling, and the digital thread. Right. So a digital twin is essentially the virtual representation of a physical asset or a process enabled through data and simulators for real-time prediction, optimization, monitoring, control, and informed decision making. So what this basically means is it is a digital version of something in the real world. A really common example is Google Maps, as Google Maps is a sort of on-the-screen representation of the real geographical locations, and it can often replicate conditions like traffic, routes, roadblocks, etc. And similarly, a digital twin in this context would be something which is a digital representation of a real-time wind turbine or other system, right? The next definition that would be important to think about is the digital sibling. Okay, so the digital sibling is essentially a special case of a digital twin where we run that digital twin in an offline setting for the purpose of scenario analysis, what-if analysis, risk assessment, and uncertainty. So a good example is a digital twin will replicate the real-life current scenario of a wind turbine, whereas a digital sibling is a special case of the digital twin where we essentially try to run the digital twin for specific, bad scenarios, like what if there's rain, what if there's snow, etc. What would we do then? So it's kind of like a way of sort of testing out situations in a virtual format. And finally, we've got the idea of a digital thread, which is the case when the predictions and other things that we know from digital twins can essentially be archived during the lifetime of the actual physical asset, and it can be used for designing the next generation of assets. So that is the digital thread. So now we're going to go into a new concept, which is the capability and the technology levels of the digital twins. Okay, so the thing is, we want to specify that all digital twins are not created equal, right? Like there are different levels at which you can simulate the functioning of a real world asset or item. Okay, so what are these levels? Well, we've got level 0, standalone. So the standalone digital twin is essentially a digital twin before the physical asset comes into existence. The value of a standalone digital twin, in addition to being used for design purposes, is that it can be used for a preliminary cost-benefit analysis of the asset before it is even built. So the thing is, you don't need the actual asset to exist to start building a digital twin. We can start, almost like a live sketch of the very asset, can help in, doing all the cost-benefit analysis, deciding where to, set up the place, etc. In a concrete case for wind farms, a standalone digital twin can be used for wind farm siting. So where do we create the wind farm? Wind turbine micro-siting, wind availability studies, or long-term climate studies. Another application is where the turbine components for each turbine are configured based on its site. So we can also try to simulate the very workings of the turbine and the configurations for the turbine based on the conditions in which they will be operating, right? So this is a sort of very premature, like standalone digital twin. Now, the next level of digital twin shows up when we actually have the physical asset, or in this case, the wind turbine, in place. So when you actually have a geometric computer-aided design model in place, and you've got a live sensor data stream coming in from the very turbine or asset in question, then this is a descriptive digital twin, which can provide insight into the inner workings of the asset at a required granularity. So this is a very powerful interface. Numbers can be shown where relevant. Critical components can be highlighted through color. Rendering priority enables X-ray vision. You've got heat maps, which allow you to look at parameters like stress, temperature, or component wear. So you've got to think something like the whole Jurassic Park situation where they are looking, when they're asset containment, and then they're like, looking through, they've got basically a model of the park going on, and they're like, oh, look, this is the heat map, this is the trace. So that is the digital twin, because that's a very dangerous place, right? So they need a digital model or description of the area without actually going and looking into the area. So that's a very similar situation, but for the relatively more realistic use case in this situation. So sensor data is typically only available at specific positions and times. So physically accurate models can help interpolate data to areas of interest. So what we're saying is we don't always know, the exact thing. So what we want to do is create models, or create almost like a function which can help us interpolate or extrapolate to a new situation. Like, maybe right now the temperature is only 10 degrees Celsius, but if we know how it works at this temperature, then we can kind of extend to how it will work at 12 degrees or 13 degrees or whatever. So it's that sort of thing. Okay, the physical asset may be too expensive, dangerous, or inaccessible for humans. So again, case in point, Jurassic Park situation. So it's too difficult to go inside the sanctuary, but it is good enough if we have a digital twin. But we also saw in Jurassic Park how the sort of concept of digital twin, that is the heat map thing, was not fully efficient because the dinosaur sort of evaded the digital heat map. Like it sort of challenged itself and disguised from the heat map. So it's very important to ensure that there's a sync between what you're trying to model and the actual, physical thing, because if there's a mismatch, as we saw in Jurassic Park, it can be very dangerous. So anyway, a descriptive wind farm digital twin. Okay, then coming to the realistic use case, which is for the digital twin in the wind farm. It can be used to remotely monitor the wind farm. Okay, because the real situation here is that the wind farms are in remote locations, and for example, we've got offshore wind farms and farms in the Arctic regions. So unless you're willing to take a trip to the North Pole or in the Arctic regions, you're not really going to be going there every now and then, and we really need a remote way of accessing the farm, right? So in contrast to the common SCADA, or the supervisory control and analysis, system, it provides. So that's a very like rudimentary type of supervisory analysis thing. But this descriptive thing can provide a 3D visualization of all the relevant data collected on the wind farm. And what that allows is for experts to interpret the data faster and for non-technical staff to understand it. Okay. Now let's move on to the next. So we've done standalone, so that's before it's even born descriptive. We've just got it in place. Now what could be the next level? Give you a pause. Okay. So the next level is diagnostic. Hope you got that right. Okay. So at this capability, we no longer just want to know what's going on. We want to be able to diagnose or find the root cause of any issues. Okay. So it's not just about this is what's going on, we're monitoring from afar. It's this is why it is going on, something like that. So in this capability level 2, data analysis tools are applied to the data for the sanity checks of the sensors, condition monitoring, and fault diagnosis. So we're looking at what's going on, why are things going wrong. Okay. It is referred to as a diagnostic DT. Based on the current state of the diagnostic DT, diagnostic tools such as the vibration detection can be employed to detect irregularities in the digital twin even before they cause failures. So maybe there's just too much vibrations or something like that going on, and therefore we know, oh no, there's something wrong in the system. Okay. Experts can then use the information provided by the diagnostic digital twin to make adjustments before minor faults result in more significant consequences. The diagnostic digital twin is especially interesting for the high-value assets such as wind farms. Reason being, it allows the detection of irregularities in the turbine before the irregularities can cause faults or unexpected downtimes of the turbine. So additionally, it reduces the need for on-site inspections, especially in remote locations. So without the digital twin, you'd be going and inspecting a lot of irregularities on a pretty regular basis. So the diagnostic digital twin is going to help you avoid all of that. So the next level will be predictive. It should be noted that the standalone, descriptive, and diagnostic digital twins do not give any insight into the future. The predictive digital twin, on the other hand, starts exploiting models to project current and past states into the future. The prediction is continuously updated based on real-time data stream from the physical asset, and with the constant update of this asset state, there is no risk of diverging too far from the physical asset over time. So in the case of the wind farms, you've got several applications. Short-term wind weather and power forecasts allow the optimization of turbine settings. So it's mainly about, we need to tune our settings on our turbine according to the power forecasts. Mid-term forecasts are required for energy trading on the day-ahead energy market. Long-term forecasts aid by estimating the revenue or even predicting the impact of climate change. Furthermore, the predictive digital twins can be used to forecast component wear and estimate the remaining useful lifetime of components throughout the wind farm, alleviating unexpected downtime. So it's not going to do anything for you, but it's at least going to tell you, look, this is how long your components are going to last. You're going to have to change it in the next year. The climate change is going to cause this and that. And you can even have the weather forecast. This is going to rain tomorrow, so make sure you do this X, Y, or Z. Change the turbine settings. Blah blah blah. Combining the weather forecast and predictive maintenance allows scheduling inspections and maintenance when there is no wind, thereby further reducing the effective downtime of the wind turbine. So it's like, let's only have the inspections when there's barely any wind in the first place, so we're not actually causing downtime for the inspections. So that's all the predictive stuff. Now continuing on, the next level is prescriptive. So we've done the predictive. Now let's do the prescriptive. So that means we're going to start supplying solutions. We've done the why, we've done the what. Now we're going to do the how, like how we're going to solve it. Okay. For optimal control of the asset, prescriptive digital twins come in handy because they make recommendations based on what if or risk assessment and uncertainty quantification. This aspect is highly desirable for decision support systems, providing recommendations to experts who then decide how to act upon them. In the context of wind farms, the prescriptive digital twins can improve on the diagnostic and predictive features, not only to provide data with which good maintenance schedules can be developed, but directly explore what if scenarios to provide optimal maintenance schedules. Okay. Furthermore, it includes uncertainty estimates to indicate how reliable the recommendations are. So it's not just like, I'm going to recommend something. I'm going to recommend that you do this, and my solution here is going to work with a 50% probability or a 90% probabilities. So additionally, the prescriptive digital twin can provide recommendations for turbine settings at the farm level to prolong component and turbine lifetime. Like, set the setting to X or Y or Z, but depending on what we need to do to extend the lifetime. Right. So this is all about providing solutions. Okay. It's saying, do the maintenance every second month. Do it on the 1st of July. I'm probably right to a X degree, like 5% wrong, or maybe I'm right with 95% accuracy. It's about being able to quantify that, how right the recommendation could be, and even on the level of prescribing certain settings for the turbine. Now, the final level takes a lot of independence. This is more of a futuristic goal for the digital twins that we're trying to get towards overall, which is autonomous. And this is when the digital twin and the asset start bi-directional communication. So as the digital twin starts, we've all heard about the digital asset, so the actual asset that is the wind farm, giving information to the digital twin, like by the sensors and stuff. But what about the digital twin starting to literally influence the asset, right? So that's like the next level of control. So what we're saying is that the physical asset updates the digital twin, and in turn, the digital twin controls the asset to push it towards the optimal set point. So the digital twin says, look, the temperature is 5 degrees. Then the digital twin, now tells the asset, oh, it's 5 degrees. Change the turbine settings to, low temperature setting or something like that. And it's like a bi-directional communication. So here's the example of that. So the autonomous wind farm digital twin allows for closing the loop on the wind farm operation. It can continuously adjust the turbine settings at the farm level to optimize turbine efficiency while taking into account current and future weather, wind speed, direction, electricity prices, wake effects, component wear, and the remaining useful lifetime of the components. With sufficient maturity, it can furthermore schedule maintenance autonomously. By exploring the use of autonomous drones and underwater vehicles, autonomous digital twins can eventually repair minor damage on its own. So it's not even like you need someone else to repair it. The digital twin is going to do the repair for you. So it's like a fully autonomous closed loop situation with the actual maintenance. Okay. So this is all very well and good. We talked about all the technological, levels at which the digital twins can be. So the next section that we're going to kind of delve into is we're going to look a bit about the industrial perspective. Okay, so this is all like theoretical stuff, but what's actually going on in the industry. So the authors of this study basically conducted a survey across several Norwegian companies who are currently deploying their version of digital twins in this industry, and they learned about what they had to say. So let's look at what the various companies had to sort of say. I'm just going to go over a couple of the companies, and you can read the paper for like the rest of them. So let's look at what 4Subsea had to say. So 4Subsea offers decision support services to energy providers based on data analytics and digital services. So their short-term goals for the digital twins were for lifetime estimate and extension of all the components on the wind farm, and their long-term goals were to shift to operational decision support for the optimized uptime and productivity. Okay, so their aim is to use data and analytics in order to increase the lifetime and the productivity of the wind farms. So what their argument is that modeling only the parts of the turbine is not sufficient, as the global loads are of main interest. Therefore, it might be sufficient to start with a complete but less detailed digital twin. So enhancing the asset with more sensors is required, but existing sensors should be utilized as much as possible. So they already extract value from a level 0 standalone to level 4 predictive. So they've done everything except level 5. The 4Subsea has a 1 degree of freedom digital twin already running. So 1 degree of freedom means there's only one parameter which the digital twin is looking at or influencing, and it's already running to capture the tower-based strain of an onshore wind farm. They're able to perform lifetime estimates at different locations of the tower, even at places without sensors. They're able to see that how long is the lifetime estimated based on the data that they're getting, especially from the sensors and even places without the sensors. And it's agreed that a similar digital twin for an offshore wind farm would be much more complex. So they were onshore, but it would be a lot more complex for offshore. So for offshore oil and gas, 4Subsea has operated digital twin models up to level 4 for several years to make short-term predictions and decision support for wellhead fatigue during drilling and workover operations using subsea motion sensors on the blowout preventer. So this is for people who are at sea. It's using subsea motion sensors. Okay, the system is also fully commercialized under the name Swim. They also have digital twins of 3 jacket platforms in the North Sea with a focus on integrity monitoring and anomaly detection, and digital twins of a floating production storage and offloading in Brazil. They implement the digital twin by creating a structural model in Orca Flex and running it in the platform for Insight.io on Azure, but comments that a polished interface between Orca and Flex and Insight.io is lacking right now. So basically, I'm as the engineer, I'm kind of looking at this at this point, and I understand what's going on. So Azure basically has a lot of different features, especially for handling this type of data that might be coming from sensors. They might be using Azure Digital Twins. It's a cloud platform, and they're essentially, they've created their own model, and they are, trying to feed it into Azure, which might be running some calculations, some analytics, some predictions, and essentially they also utilize machine learning models to make future predictions. The reason 4Subsea's digital twins are not more complex yet is due to the lack of time and effort in system identification and model tuning of the digital twins based on measurements. So this is a very data-focused, place, and again, they were using the digital twins, with Azure. So the next is Anio. Anio is a Norwegian company within upstream renewable energy production and downstream green energy consumption. They use new opportunities digital twins offer to reduce the cost of renewable power production within wind, hydro, hydrogen, biogas, and solar. The most significant benefits of digital twins for power production are expected to come from the reduction of downtime and increase in the technical availability of the assets. Additionally, digital twins will give insights into the decisions of prolonging the lifetime of wind farms. So they generate value from the diagnostic level 2 DTs onwards. So basically, these are people who are an energy company, and they kind of want to use these digital twins to reduce the costs of all their power plants, okay, including wind, hydro, hydrogen, biogas, etc. And their whole theory is that the digital twins are going to help them with reducing downtime, and they're also going to make the uptime more efficient. So just like the other guys, they were trying to predict the maintenance, they were trying to predict the lifetime. These people are trying to save costs. They're all cost focused by reducing the downtimes, and they also kind of additionally want to generate this, decisions on how long the wind farms are going to go on for. So they generate value from the level 2 onwards, and they also kind of focus on implementing 3D visualization to help people understand what's going on really. So in addition to the development of digital twins, they put a lot of effort into data management and bundling. They've developed digital twins with predictive capabilities for the main components in the drivetrain of wind turbines. And he was interested in autonomous digital twins, but they still believe in some human input before a final maintenance decision is taken. They assume that digital twins will aid the workforce by reducing the time troubleshooting takes inside the wind turbine. From their perspective, the biggest challenge is to build a system that provides confidence, inspiring results in daily operations. Now, the thing that I want to talk about here is that we're in an era now in 2026 where Gemini, ChatGPT, all of this is so much more mature. And I feel like in 2023, when this paper was written, it really wasn't at a level where people's results. Sorry for the brief cut. So the point that we're trying to make here is that Anio, in addition to developing the digital twins, is putting a lot of effort into the robustness of data management and bundling these as essentials to achieve reliable results. So as I was saying, back in the day of 2023, the Gemini, all this ChatGPT agentic AIs were not as well developed. So inspiring results was a lot more difficult. But now with the widespread availability of these technologies, I think it will be a lot easier to provide more confident results. So that's definitely a factor that we need to take into consideration. So the next company in question was Cognite, and they were a global industrial SaaS company driving the full-scale digital transformation of asset-heavy industries by providing simple access to trustworthy and contextualized data. Their flagship product, Cognite Data Fusion, leverages digital twins to empower anyone to use data to solve industrial problems with speed and ease by combining data in simulations and predictions for improved decision-making. The most important features of a digital twin are the what-if scenario analysis and autonomous decision-making. Modeling only parts of the assets is disfavored as the focus should be on holistic assessment. They expect that additional sensors, for example, strain gauges for the analysis of structural loadings, will have to be installed on the asset in addition to the already implemented sensors. According to Cognite, they have an operational predictive level of 3. Digital twin level of level 3. It generates value from level 0 onwards. Their current challenge is developing and further improving the what-if scenario analysis. Convincing original equipment manufacturers to override the control parameters through a digital twin is what Cognite anticipates as the biggest challenge for the future. So, this may not be such a challenge anymore, again, because, with the age of AI and whatnot, overriding control parameters through a digital twin is analogous to using AI for these purposes, so maybe the acceptance will be a lot higher. DNV Maritime. They are also part of the maritime industry, and they want to digitalize oil, gas, and offshore wind. And the most important aspects in their case are, again, 3D visualization. They can already extract from the level 0, but they want to also have additional hardware, and they're also looking for the whole what-if situation. They expect their biggest challenge to be end-to-end value chain support, and the existing digital twin is limited by lack of business and operating models. So back in 3 years ago, there were a lot of lack of business and operating models. So they're assuming that good standardization, and the important standard here is ISO 15946. So that's sort of their plan. The next one is DNV Energy Systems. They're an energy consulting company, and their goal for digital twins is to digitalize the wind turbines for condition monitoring and future prediction. Value is expected to be generated with level 3 onwards, and they use the DNV forecaster platform to predict energy production based on historic and live data. The biggest challenge is the development and capability to respond to customer requests during the initial phase. They recommend putting less focus on the algorithms and instead focusing on the implementation, including software development and intermittently and inconsistent data, which requires significant investment. So their whole focus is on implementation, handling the intermittency of data, inconsistency, etc. And so that's what they're all about. They're an energy consulting firm. And we've got Idle, and we've got a bunch of other places, and I think it's all pretty similar. I think you can look through the book for the rest of them. Sorry, look through the paper, and a lot of them, they're all concerned about the what if scenarios, and they have very similar kind of issues. So I'll leave the rest for yourself to read if you want to get the further insight. But let's move on to what are the common challenges that are being faced, by these people. So the first challenge is data. Developing a digital twin for wind energy requires real-time data exchange between the physical asset and the digital twin. However, various data-related challenges hinder the development of an ideal digital twin. What are these challenges? Data quality, data sharing, big data, and more. So let's go and look at these a bit in detail. So if you look at data sharing, data collection and distribution involve multiple vendors, So data sharing is an advantage to their competitors. It's a tedious job to reach a data sharing agreement due to the involvement of multiple players from the development through to operation and the decommissioning phase of wind farms. It was realized that wind farm owners might not even have access to the data from their own wind farms. Furthermore, if the data owner wants to share the data, they must revisit the original agreements with multiple players involved to ensure that no clause in the agreement is breached, and this delays the timely extraction of value from the data. This is all relating to the data sharing and policies, right? The next aspect is data quality. So to ensure the precise and accurate behavior of the digital twin, data quality is a prerequisite. However, duplicate, missing, ambiguous, inconsistent, asynchronous, and inaccurate data creates obstacles in realizing the ideal digital twin. Big data. You've got the whole traditional 10 years volume, veracity, variety, blah, 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 vocabulary, venue, vagueness. So whenever you've got big data, you've got problems, right? So this is the issue question, the data silo. So the fact that a lot of the times the information is just limited to one place, one wind farm, that sort of thing. So different vendors may use different proprietary standards, data formats, and tools for acquiring and accessing data, making it difficult for other vendors to extract value from it. The data silo issues result in an incomplete overview of the asset performance, hinder collaboration, and lead to inefficiencies because you've got a lot of people doing their own thing with the data. There's nothing standard across the board. Lack of systematic data collection. People are using different instruments, different components of wind farm. Very little thought is put into the optimal placement of sensors. This results in either redundant data being recorded or no data being recorded. Sparse data due to very expensive instrumentation. Data recorded might be very sparse in time and space, and a paradigm shift in the analysis is required to generate value from sparse data. Lack of centralized expertise, compute power, bandwidth to extract value from data. Even when all the above are resolved, the variety of data will require human resources trained in a wide variety of expertise to generate insight. Furthermore, huge computing power will be required in one place. The security, ensuring data security is a major challenge, and there's also the right choice for data management solutions and a talent gap. Modeling. So the data collected from an asset has sparse resolution in space and time. Moreover, they are available only for the past and current situations, thus imposing challenges in instilling physical realism. So we don't know a whole lot about it, what we're saying. Models can help improve the resolution of the data and at the same time provide insight into the future state of the asset. However, before the full potential of any modeling approach can be exploited in the current context of the digital twins, some model-related challenges need to be resolved. Based on the survey, they present some of the most desirable characteristics. So from a model, we want it to be pretty accurate. We want this to essentially be very close to reality. The model's accuracy and uncertainty can suffer in absence of a complete understanding of the underlying cause driving a phenomenon. Simplifications arising from the need to make models computationally efficient, uncertainty in the physical parameters input to the models, and numerical errors. While standalone descriptive and diagnostic digital twins reliable measured data can help improve the model's accuracy and certainty, for predictive and prescriptive, a lack of observed data complicates things further. Computational efficiency. One can afford to run computationally demanding models in a standalone digital twin. However, you need to be efficient. The need for real-time modeling in predictive digital twins and the need for better than real-time modeling for control and optimization makes computational efficiency even more desirable. Computational efficient models will also be desirable when running on standalone hardware like a portable VR set with limited computing power. Generalizability. So what this means is the ability of the model to solve a wide variety of problems without any problem-specific fine-tuning. An asset encounters a wide variety of scenarios during its lifetime. Some of the events are rare and others are persistent. The digital twin is required to model all the phenomena to be in sync with the asset, and so the model should be able to generalize their learning without any compromise on efficiency or accuracy. ever evolving. A model that is specialized for a narrow range of scenarios loses its accuracy when encountering new situations. So we need this model to be able to learn and evolve every time a new scenario is presented. And this is especially relevant in cases of exceptional circumstances, like impending hardware faults. And then we've got interoperability and trustworthiness. A model is considered interpretable when humans can readily understand the reasoning behind these models. The trust and transparency of the digital twins has to be one of the biggest challenges. So we really need our digital twins to make decisions in a way that humans can understand why the heck they made the decisions. A black box model might detect a fault in the turbine, but it requires an interpretable model to pinpoint the exact cause and plan the countermeasures. Robustness and stability. Robustness and stability of the model are critical factors in determining how reliable it is. A model that is robust and stable produces consistent results even when subjected to perturbations. In contrast, a model that is not robust may show significant deterioration when faced with noisy inputs, while an unstable model might fail for certain modes. Therefore, robustness and the stability of a model are essential requirements for ensuring that it's reliable. Now, the existing approaches can typically be grouped into three categories: physics-based, data-driven, and hybrid modeling and analysis. Every approach has its own benefits and its weaknesses. The high-fidelity physics models are associated with high computational effort. So the physics-based ones are very high in computational. But the data-driven models may not be high computational, but you can't really understand why they do what they do. So what they're saying is it might be easy to tell Gemini, can you, predict, but Gemini may not fully, properly pinpoint the exact thing, or at least in the 2023 context, right? In the survey, it became evident that the industry needs to generate value from the data, while also being able to utilize existing knowledge to the maximum extent possible. To this end, multiple companies argued in favor of hybrid analysis and modeling to compensate for weaknesses of both physics and data-driven modeling, and they recommended academic research to focus on this area. Now, in section 4, we give examples of physics-based, data-driven, and hybrid analysis and modeling techniques, their application within wind energy, and their strengths and weaknesses with respect to each other, and with respect to their applicability to digital twins. Digital industrial acceptance and trust for digital twins. Now, the next big challenge is that there's not that much trust even within the industry, okay? First of all, not everyone even agrees on what a digital twin is. There's currently little consensus on what constitutes a digital twin. And this lack of a clear definition can lead to confusion and mistrust among industry professionals and the general public. It's important to establish a common understanding of the term and its applications in order to build trust and awareness. Little awareness about the values that digital twins can generate, okay? So people don't really even know about the potential benefits of digital twins, such as improved efficiency, safety, reduced downtime. We need to educate stakeholders on their value to build the trust and acceptance. Technology readiness is insufficient. Sustainability readiness. Despite the potential benefits, the technology readiness is not yet sufficient for widespread adoption. There's a lack of focus on sustainability readiness. While it's essential to ensure that technology is environmentally and socially responsible, addressing these concerns is crucial in gaining industry acceptance and trust. Lack of appropriate business models. There's currently a lack of appropriate business models for digital twins, which can make it difficult for companies to justify the investment. The development of viable business models will be key for gaining the industry acceptance and trust. Security and privacy. The use of digital twins raises concerns about privacy and security, especially in critical infrastructure such as energy, transportation, and healthcare. It's important to develop robust security and privacy protocols to gain industry acceptance and trust. Enabling twin projection. One of the key benefits of digital twins is the ability to project and simulate the behavior of physical assets. However, this all requires accurate and reliable data, which may not always be available. If we need industry acceptance and trust, we need to develop reliable methods for enabling twin projection. In summary, these digital twins have a lot of potential to revolutionize many industries, especially the wind one. But to gain the trust, we need to resolve these particular challenges. Now, we've discussed the problems. What are the solutions? Now, I'm just going to go in a brief overview over the solutions. All right. So, how can we solve the problems that we discussed in the prior slides? So the first thing we want to do is think about standards and the asset information model. So what we're saying here is that multiple companies can be involved in a digital twin over its life cycle. Okay, so we start off with the component manufacturers, and these people use the data from any previous digital twins, like for example the digital thread, to improve the component design, and they might provide a digital representation of that component. The OEMs use their overall reference design designation structure together with operational data from previous designs to provide an updated and improved digital twin as the basis for a new design, sizing, construction, and logistics. Maintenance crews might be employed by different companies. The energy distribution industry benefits from increased reliability and may use forecasts to stabilize the grid. Other companies might be involved during the decommissioning. In addition, all the companies can generate value from the data recorded during operation. And finally, industries might be interested in collaborations to exchange data and digital twin structures for mutual benefit. So what we're talking about here really is that there's a lot of different companies involved in the entire life cycle of the digital twin and of the wind farm. So there's a lot of data that's very valuable that can help people construct, and even the destroying and creating new things. So the situation here is that we need to provide a standardized way of exchanging information between all these different parties. So that's why we need a standardized asset information model. Okay, so the asset information model is the digital representation of an asset that contains all the relevant information throughout its life cycle, from the design and construction to operation and maintenance, right? It's a structured collection of data that captures all the necessary information about an asset, right? So this thing is talking about everything you need to know of the asset. It's a bit like a Wikipedia page, but for the asset, including its physical and functional characteristics, operational requirements, maintenance history. So you know how like Wikipedia is a standardized way for you to look up anything, right? Like it's a standardized way for you to take in information. It's got a standard structure. So something like that, except, imagine a wiki dictionary for assets. So that is the asset information model. So it may also include information about the environment in which the asset operates, such as the weather patterns and the local regulations. The purpose of an asset information model is to provide a comprehensive and integrated view of an asset, enabling better decision making and more efficient in operational and maintenance. By capturing all the relevant data in a single location, it can help asset owners and operators to optimize asset performance, reduce maintenance costs, and extend the asset lifespan. However, despite the obvious value, little work has been done for this. And people have not created that Wikipedia page, is what we're saying. Fan wiki dictionary, whatever, right? That has not been done. We in the following section present some preliminary work done in this direction by DNV. So that's one of those companies. Structures and standards have been strongly influenced by the flow site proposal in North Wind project. So we've got like a reference designation system. So they've got like this entire convention around naming and structuring the assets and workflow components. So it's ISO something, called RDSPP, and RDS is already used in wind farms. We've got a reference data library, which contains static or slow changing data elements of the system, including conversion factors between units, physical constants or country codes. Semantic data model, the meaning of data instances is described. There's a working draft for part 14 of ISO 15926. It represents a industrial top level ontology based on 5 years of experience. Information exchange and application interfaces. Some standards which are relevant here include the ISO 10303 for product data exchange, or STEP standard for the exchange of product model data. Here we have the CAD model exchange, IEC 61968 for the informational exchange between electrical distribution systems and all that, the digital twin environment, and other required standards. So there seems to be some useful information here, which is like simulations for the wind farms have been done before, but you're going to have to handle large amounts of input data and perform simulations in real time. It has to be assessed if existing platforms can be adapted to this new situation, or if specific digital twin environments have to be created. An example of such a platform is the Open Simulation Platform, which has been built by DNV, Kongsberg, Syntef, and TNU. During the survey, Microsoft Azure Digital Twins have been mentioned multiple times for hosting the digital twin. So I am not wrong here, it was the Microsoft Azure Digital Twins. However, there are more specific products, which are also involved. So we're talking here about standard environment for the digital twins. We've seen Azure Digital Twins being used for hosting stuff. We've also got the Open Simulation Platform, which is being built by like a bunch of these companies, and there is definitely a lot going on here. So while the above mentioned existing standards provide a basis, digital twins will require additional standards. This includes standards for data compression, standardized connection between data, models, analysis tools, interfaces. Based on these standards on existing ones will improve industrial acceptance. Okay, so as a data engineer, I think I can kind of comment on this. This is the kind of place where I would like go in and talk about using existing standards for data compression. I would say use Parquet, use Delta tables, standardized connection between the data, Kafka for big data streaming. Like this is the kind of place where you would use those typical data engineering things to bring about the data standards. So that's just my 2 cents from the data engineer sort of like angle on the whole thing. So the next thing is data acquisition, communication, sharing, and archival. In digital twins, data from as many sources are combined to build a realistic as possible virtual representation of the physical asset and its environment. Some information like the architecture and design is usually static and can be inserted manually. Most information such as wind speed, temperature, wave height, and loads are changing constantly and have to be updated in real time through sensor measurements. The collected data is then compressed, augmented, and or analyzed with physics-based or data-driven models. PBMs, or the physics-based models, make use of domain knowledge, such as the fundamental laws of nature. Data-driven models, on the other hand, are built and trained with a large amount of data from physical assets in the past. In this section, we address both real-time and historical data, and we discuss modeling techniques. So this whole section of the paper is all about, the physics-based models and the data-based models. And, this is all about, data acquisition, communication, sharing, archival, all of that stuff. So I think the first thing that they're talking about here, this is super important, I think, is the sensors. Okay, now all of it is all about sensors. When the industry in general agreed that at some point additional sensors will have to be installed, some companies argue that the currently installed sensors can already be used to build digital twins, thereby reducing the monetary value entry threshold of digital twins for wind farms. So it's not that we necessarily need new sensors. We could reuse the existing sensors in the wind farms to do the digital twins. The variety of sensors usable in wind farms is enormous. Heat can be measured through temperature sensors and indirectly provides information on friction, on gears and bearings, right? Acceleration sensors, they allow vibration measurements and they can provide information on component wear. Microphones measure the vibration through the air. Tower loads and strains are measurable with corresponding sensors. Oil quality can be monitored. Air and water corrosion can be tracked through air and water concentration measurements. And precipitation measurements contribute to blade damage estimation. Specifically interesting for the wind fields and therefore farm control are the LiDAR systems. Dan, I remember the LiDAR, light detection and ranging sensors. They use lasers and the Doppler effect to measure the wind speed. They can be mounted on the nacelle or on separate buoys and can be used to tell the speed of the incoming wind, as well as to measure the wake effects. This helps to model an accurate wind field around and within the wind farm, which can then be used to improve the accuracy of the wind impact on each turbine. With the success of machine learning, so now we're coming to AI again, in image recognition, this is the whole CNN models, blah, blah, blah. It's going to come up. So, cameras provide a valuable measurement technique in combination. So they also reference another work where dynamic mode decomposition and 2 neural network models were used to identify the movement and rotation of objects in recorded images. So the technique can be generalized to spot environmental changes in wind farm and its vicinity, be it buoys or boats in offshore farms or agriculture or forestry on onshore peaks. Optimal sensor placement. The sensor positions are the basis for accurate data acquisition. Through a sophisticated design of experiment, DOE, the number of sensors can be minimized, while measured information is maximized. So in the above section, we were really talking about how you could use different sensors and low-cost ways of measuring things. And now we're going to talk, so these sensors are really key for us to get an idea of what's going on, right? Now, what do we need to know about these sensors? We need to place the sensors in the right place, otherwise it's going to be useless, okay? The sensor positions are the basis, and you can use the design of experiment methods to minimize the number of sensors and maximize the amount of information that you get from the sensors. In a holistic level, 1+ digital twin of a wind farm, digital twin wind farm measurements for fatigue loads at towers, foundations, blades, and drivetrains have to be performed, okay? Sequential sensor placement. So they talk about a work where a sequential sensor placement algorithm is used by minimizing the information entropy of the relevant quantities. So this is interesting. So there can be literal algorithms that you use to discover like where to put the sensors and literally minimize the information entropy. So entropy is like the distortion. Okay, literally place the sensors to reduce the amount of chaos in the information that they give. It maximizes the accuracy, but also considers the installation cost of the sensor positions to determine the strain time history and tower jacket support structure and soil stiffness of an offshore wind turbine. The algorithm has to be used differently for parameter estimation and strain estimation. In another work, the authors investigate the optimal positioning of sensors for fault analysis in turbine gearboxes based on statistical features and data-driven methods. Their algorithm is tested on a lab scale, and they're able to reduce the number and increase the fault detection accuracy of the sensors, but they note that their method needs further investigation on different datasets. In another work, the optimal placement of a given number of acceleration sensors for the static modal analysis of the blades is determined using a multi-body approach. 3 different algorithms were tested on a 3 megawatt onshore prototype by using the modal shape matrix and testing the results with the automodal assurance criterion. A genetic algorithm with a weighted off-diagonal criterion identified the sensor positions with the lowest linear dependencies measured between measured modes. So this is a place where we are talking genetic algorithms. We're talking like the whole ant model, all of the stuff, okay? This is the GA algorithm stuff of the legends, okay? This is the stuff that they are using to position the sensors optimally and to avoid any problems. So people can use these algorithms in a product to discover where to put their sensors. The next thing is reducing data size. Through the number of sensors and high measurement frequencies, the data stream between physical assets and digital twins can be rather large. Compression and decompression of the data can help to reduce the required bandwidth and storage space. Compression techniques are applied before the data transmission is performed, and decompression is used before using the data. Other techniques reduce the amount of sensor data transmitted or the measurement frequency. Commonly known lossless compression algorithms making use of the file string include LZMA. So we are talking about compression algorithms or compression techniques to reduce the amount of data in question. Okay, very nice. So they're talking about 7Z. Have they mentioned Snappy? Nope. They use features like identifying identical strings, LZMA, the Lemkel-Ziv Markov algorithm, deflate BZIP2, GRIP2, general regularly distributed information in binary form, tested for wind and wind speed data, principal component analysis, the PCA, eigenvalue thing, enables the reduction of the dimensionality of the data to the components with the highest variance. We all know about this. Obviously, you're going to have like so many different features. We only want to identify the features which have the most differences going on. They're the most essential ones. That's the PCA, eigenvalue, all of that stuff. Autoencoders is another thing. They perform neural network-based compression. The input and output layers have the size of the data, but at least one of the intermediate layers is smaller in size. The neural network is trained to output the input data. Afterwards, the neural network is split at the smallest layer so that the first part can be used as an encoder and the latter one as a decoder. Generative adversarial networks are another one. The generator tries to reconstruct the original data. Discriminator tries to separate both the reconstructed data and the original data by training both against each other. So we're talking a generator and a discriminator. Generator is doing the reconstruction, and discriminator tries to separate the reconstruction and the original. And essentially, generator wants to be training it. So by training both against each other, so the discriminator needs to stop being able to distinguish them really. So and then the generator is trying to make something more and more close to the original one. So when you do that, even data with unknown compression algorithms, they can be restored. The drawback of NN-based methods is that they are only performing well on the parameter space on which they are trained. If the sensors record unexpected data, for example, from damage to the farm, they will not be able to recover the data after compression. However, this reconstruction error can be monitored by performing decompression on the farm and comparing the accuracy of the data. Fault detection is done with autoencoders and with conditioned variational autoencoders. Compression sensing can be done for sparse signals, for example, signals in which there is a domain so that the signal is only represented by a few non-zero components, to recover the original signal from a reduced frequency of data points, allowing for the reduction of the sample frequency and thereby the data size. This can be combined, for example, with the fast Fourier transformation for periodic signals. In another work, compressed sensing is utilized to reduce the amount of transmitted data by predicting sensor data and only requesting sensor updates when a category of sensor data differs from the predicted one. Under the assumption of frequency compressibility of the periodic impulsive component, another work applies the compressed sensing for the wind turbine gearbox to recover the impulsive features from fewer data points than conventionally required using the Shannon sampling theorem. Virtual sensing is a technique used to infer the value that a sensor would measure from data recorded with other physical sensors. Physical sensors are therefore not required at points of interest, but they can be placed in positions where they gain maximum info. So what we're saying is you can even literally have like a non-existent sensor which uses the existing sensors to get info about points which are not in the sensors we met. So this allows for reducing the total number of sensors and inferring values at places where the sensors can't be installed, and for inferring unmeasured quantities. Note that a physically realistic model is required to enable virtual sensing. The authors in another work use PCA for virtual sensing of strain estimations on an offshore tower, using temporary sensors for model calibration. A large number of compression techniques and use cases outside the wind sector are listed. So for data security, we're looking at blockchain technology here, which is a really good opportunity for blockchain. And data is chained in like blocks through hashes, and they have a hash of the previous block. We've got consensus algorithms if something has been changed. So blockchain used to build a safe wind farm information system is being investigated. Data sharing, how huge amounts of data are generated in every wind farm. However, the amount of openly available data is puny, especially from the SCADA type systems, which are not readily available. This is partially attributed to the way proprietary rights are handled in wind farms. This became especially evident in the industry survey conducted here. It was commented on multiple times that the proprietary rights of the OEMs are causing problems even for the operators of the wind farms themselves. It's hinted that the OEMs are keeping the proprietary rights to secure their designs and expand their market to analysis and operating software. This heavily influences both the development and application of digital twins and related technologies such as predictive maintenance. Future will show whether digital twins will cause increased data sharing, or the OEMs will be the only ones offering digital twins for their assets. Modeling and analysis, right? So really there is a lot of stuff going on, okay, with the physical ones, and you've got a lot of different ways in which the physics-based models are going to work, right? And this is largely based on computational fluid dynamics, structural dynamics, okay? So fluid dynamics, we're talking the flow of air around wind turbines, okay? We're talking aerodynamic performance. Structural dynamics, we're talking about the response of wind turbines to turbulent wind conditions, such as gusts and eddies. Aeroelasticity. We're talking a detailed review of aeroelasticity in the context of wind turbines. In wind energy, aeroelasticity models can be used to study the dynamic behavior of the wind turbines, including blade deflection and tower vibration. Wake models. They are used to study the behavior of wind wake downstream of a wind turbine. In wind energy, the wake models can be used to predict the impact of wind turbines on surrounding environments, such as on wind farms and local wind resources. Electrical models. They're used to study the generation, distribution, and storage of power. In wind energy, electrical models can be used to optimize the performance of wind turbine generators and to study the integration of wind energy into the electrical grid. Degradation models. Degradation models are used to study the long-term performance of systems, including the effects of wear and tear, aging, environmental factors, etc. Now, the thing is, in the standalone digital twins, they don't need to be evaluated online, and the requirements for computational efficiency are a lot less. They can be used in standalone in the design and planning phases. And one major focus of the physical-based models in this stage is the blade optimization. The turbine blade design is being optimized with CFD modeling software in one of the works. The authors of another work use the Reynolds average Navier-Stokes technique to investigate the geometric approximations of the blade segments on the aerodynamic performance of the wind turbine. There are other people who investigate fluid structure interaction using isogeometric analysis and non-matching fluid structure interface discretization on an offshore reference wind turbine rotor. And another important design in the initial stages would be the farm layout, which depends on local wind resources and wake effects. And you can use CFD methods to optimize the design of a wind farm in a complex terrain, validate the offshore farm model against the operational site, and another one uses the wake growth rate using a Gaussian wake model. And then in level 1 with the prescriptive digital twin, so descriptive one, this is a situation where the PBM alone is inevitably going to drift away from the real state because of the approximations and external influences. Data, on the other hand, will not describe, and that's also pretty sparse, and it will not describe the wind farm and its environment in sufficient detail without models that can interpolate in space and time to infer parameters. So both data and models, so both data and the physical ones, need to be combined, okay? So the deviations between the physical models can be alleviated by measuring data and by using them as input to the physical models for boundary conditions and reinitialization. Strategy is already being used, for example, to nest wind flow models into meteorological forecasts. A critical condition for using them in descriptive and higher models is the execution speed. Models that cannot be evaluated in real time cannot be used for the digital twins above the standalone level, since they cannot keep up to date with the asset. Approximations can reduce computational efficiency at the cost of accuracy. When choosing PBMs for digital twin applications, a trade-off between speed and detail is imperative. Now, on the level 2, okay, with the diagnostic one, using the real-time data and the spatiotemporal resolutions, the condition of the wind farm can be monitored and diagnosed. In the context of descriptive DT, the physical models are especially interesting for degradation estimation for all the wind turbine components, from blades to bearings, over the drivetrain, gearbox, the generator, the tower, the foundation structure, and the floater. One of the authors of a work explored the feasibility of a novel low-cost mechanical displacement indicator to continuously monitor tower movement relative to the foundation base, and suggest that a combination of measurements and FEM would allow identifying the foundational issues. In another work, a multi-scale progressive damage model was implemented by combining computational micromechanics and continuum damage mechanics in a FEM to predict subcritical microscopic damage evolution and stiffness degradation in turbine blades. In a following work, a digital twin condition monitoring approach for drivetrains is implemented by estimating the RUL through online measurements and fatigue damage estimation. It's clear that due to the inherent weaknesses associated with the ignored physics and uncertainty in input parameters, the diagnostic characteristics cannot be relied upon. So we're saying that the pure physics models kind of fail, in like the real world. Now, the physics-based models and the predictive digital twins, they can include predictions of wind, weather, power output, turbine motion, temperature, loads, fatigue, all of that stuff. Now, one of the authors of a work reviews wind power forecasting models across multiple wind farms and countries. A multi-scale wind model is used to predict wind flow on wind farms. The meteorological predictions of the model are integrated into a digital twin to infer turbine and farm power production and explain the predictions in a virtual reality interface. Another thing you've got is the physics-based model in prescriptive digital twins. On the prescriptive level, the demands on execution time of integrated models become even stronger, since many what-if scenarios must be explored simultaneously to obtain uncertainty estimates and provide simultaneous optimization recommendations to the user. Even with parallelization, computational efficiency is a huge challenge, okay, for these physics-based models. But if you speed it up enough, they can be used as an input for optimization and uncertainty estimates. The prescriptive digital twin can be used for decision support in scenarios where human operators have enough time to compare the value of the description with their own domain knowledge and react. Maintenance scheduling is one such example where degradation and damage propagation models are required to analyze the risk and reward of timely or delayed maintenance while taking into account weather conditions determined to identify optimal maintenance windows. Therefore, fast diagnostic and predictive models are required as input into the scenario analysis of the prescriptive component. It's worth noting that the tools that enable standalone prescriptive and diagnostic digital twins can be used in the prescriptive settings also. PBM and autonomous digital twins. Now, the autonomous digital twin can be used for applications that require continuous optimization, or where the human operators do not have enough time to react, and for applications that require continuous optimization. In some cases, model-free control can be sufficient, but reliability in complex scenarios argues in favor of model-based controllers. Like the prescriptive digital twin, fast and reliable models are needed as input for these controllers to optimize the control process. Despite their utility, due to partial understanding and numerous assumptions along the steps from observation to the solution of these equations, a large proportion of the important governing physics gets ignored in the PBM approach. Even the applicability of high-fidelity simulators with minimal assumptions has so far been limited to the offline design phase only. Despite the major drawback, what makes these models attractive are the sound foundations from first principles, interpretability, generalizability, and the existence of robust theories for the analysis of stability and uncertainty. Unfortunately, most of the accurate physics models are generally computationally expensive and do not automatically adapt to new scenarios, and they can be susceptible to numerous numerical instabilities. So the point here is that, the physics models are not robust enough to automatically, change or like do changes all on their own. So that's where we come to the data-driven modeling. Okay, so we talked about the physics-based models, which are all about using the physics concepts. But now when we come to the data stuff, we are talking about all these different machine learning algorithms: supervised deep learning, unsupervised deep learning, supervised linear models, supervised nonlinear models, unsupervised nonlinear models, unsupervised linear models. So these are all the broad categories of the machine learning that can be used to basically capture all the different stuff. So you've got supervised linear models, which use techniques like linear regression, logistical regression to predict things. You've got like the whole PCA, linear discriminant analysis, that's unsupervised, it's like cluster and situation. You've got the supervised nonlinear, like the support vector machines, random forest, decision trees. So those are the type of things that you see when you want to make a decision on based, and then you have several decision trees. That's like a whole random forest thing. And then unsupervised nonlinear, you've got the self-organizing maps and the autoencoders. So these are nonlinear models which are trained using unlabeled data. So unlabeled means data for which you don't already have like a target classifications. So we're basically trying to, for example, that was the whole compression thingy that we were talking about before. Supervised deep learning, this is for the image and that type of thing. So like you've got the convolutional neural networks, image recognition, recurrent neural networks, all of that stuff. Unsupervised deep learning models using the unlabeled data, for example, the GANs, the generative adversarial networks, autoencoders for data compression, all of that stuff. And then you've got data models in standalone. Standalone does not have a data stream, but it's used in the design phase, and it's really suitable for like the consideration of risks like wind conditions, wind density, all of that, how it can play a role. But the data may not always be available, so that's one fact. In the descriptive one, so let's have like a brief overview of the kind of stuff they did here. You've got works that use genetic algorithms, dynastic optimization algorithm, particle swarm optimization, cyber swarm algorithm for microsighting, for wind farm layout. You've got like, standalone DT being very useful for various wind energy related applications, all of that stuff. For the descriptive digital twin, you're using the principal component analysis, generative adversarial networks, autoencoders, all of that stuff, which doesn't just rely on sensor data, but it's able to estimate quantities between the sensors and derive quantities through models. Physics-based high fidelity models require significantly larger computational resources and are typically not able to run in real time. It's especially true for fluid dynamics. It's important to note that the descriptive DT does not only use simulations, and they have to be applied to enhance measured data. For example, you've got the resolution of images through the GAN, and a significant drawback of the data-driven models is that you can't really generalize it to anticipate the unanticipated situations. And then now if we move on to level 3 with the diagnostic one, you've got data-driven models where it triggers alarms like in different conditions. So for many cases, data-driven models can capture the complex physical behavior, and in the context of wind power, we apply the PCA, calculate the test statistics, and Hotelling's t-square. If it becomes too large, the reconstruction-based contributions are calculated to identify responsible parameters, and then you can also use the Fisher discriminant analysis and monitor deviations through test statistics. Furthermore, neural network-based techniques such as autoencoders and denoising autoencoders are considered for fault detection. Here the assumption is that they're able to capture complex connections between inputs that simpler models cannot identify. In autoencoders, the encoder compresses the input information into a vector smaller than the input and output vector. If the input is not covered by the training set, for example, the turbine data under usual fault-free conditions, there's a risk that the decoder is not able to reconstruct it. By defining a reconstruction error, the amount of difference between the input data and fault-free data is quantified. Should this reconstruction error become too high, a potential fault is detected. A DAE purposely corrupts part of the input for higher accuracy. This approach is used, for example, on SCADA data. There is another work which uses the GAN, the generative adversarial network, for self-setting reconstruction error thresholds. The GANs and Siamese encoders are used to transfer data to reduce the impact of ambiguous training. So we've got all these things which are trying to like train the model to deal with, not so great data. DDM in predictive digital twins, it performs the forecast by extrapolation. Using variables that we could forecast would be the wind speed, direction, turbulence, produced power, remaining useful lifetime or rule of the components, or even the impact of climate change on the farm. The timeframes can range from seconds to decades. In either case, forecasts are frequently performed with data-driven models based on a given time series. Some simpler data-driven models are, for example, autoregressive and moving average models, or a combination of those with exogenous variables and seasonal effects, trend removal through differentiation and integration, or prediction of multiple series simultaneously through the vector inputs. The ARIMA model, a combination of the above-mentioned techniques, is used for wind speed modeling. There's another work which uses the SARIMA and the NN-based model for daily power wind forecasting. The neural networks have been used to include complex connection between the data points for this whole predictive thing. ESRNN, you've got like all these things, multi-layer perceptrons, convolutional neural networks, recurring neural networks, KNNs for wind speed forecast. And now for the whole prescriptive things, we're done with the predictive, using the NNs. Prescriptive to give the recommendations. Recommendations, must be sufficiently long-term oriented so that humans can react to them. This could include recommendations for when to do the perform maintenance and other things. Many recommendations require control algorithms. Control algorithms are based on or supported by physical models. An advantage of data-driven is that they do not depend on a model that can be potentially flawed, but they typically take longer to converge and to produce the required outcomes. Now, lastly, we come to the data-driven models for the autonomous. So it's pretty similar without human interference doing the decisions. Data-driven have been applied to wind farm wake steering in simulations. Examples include gradient descent and game theory. While at earlier DT levels, there's always a human confirmation. This is going to be fully autonomous. Every decision must be absolutely safe and reliable. The black box nature of data-driven models makes it very difficult to guarantee the required reliability, and indeed, to the best of our knowledge, there have been no proof of concept tests with data-driven farm-level controllers on real wind farms. However, a reinforcement learning NN has been recently applied to a real hydrogen fusion reactor for plasma balancing, which proved that data-driven controllers can be operated even in safety-critical environments. Note that the reinforcement learning algorithm had gone extensive training on a high-quality physics model. Some of the advantages of these models are online learning capability, computational efficiency for inference, and accuracy even for very challenging problems as far as the training, validation, and test data are prepared properly. However, due to their data-hungry and black box nature, poor generalizability and inherent bias, a lack of robust theory for analysis of model stability, their acceptability in high-stakes applications like digital twins and autonomous systems is fairly limited. In fact, numerous vulnerabilities of deep neural networks have been exposed beyond doubt in several recent works. Hybrid analysis and modeling. So the thing here is we need to instill physical realism. One desires to have the following characteristics. You want to have accuracy, efficiency, trustworthiness, generalizability, and self-evolution, for which you kind of need a combination of both. Trustworthiness, self-adapting, all of that. So physical ones can achieve high fidelity, but at computational cost that is not available. CFD-A's detailed simulation modeling often requires weeks or months of computing time on high-power computing clusters, and furthermore, physics-based models are not self-evolving, but pretty much pre-programmed. The data-driven ones are typically faster, but they're black box, especially in safety-critical situations, and furthermore, they're applied to very specific tasks, and once trained, not able to generalize. And finally, while data-driven models like reinforcement learning are self-evolving, they're based on trial and error, which cannot be allowed in a real environment. A brief comparison of the physics-based and data-based will be given. So fortunately, a new paradigm for the entire thing called hybrid analysis and modeling, combining all of the stuff, is now available and it's emerging. So it's called grey box models and hybrid semi-parametric models, which fall into this. While certain approaches have been investigated for decades, their popularity and impact have increased as data-driven models are becoming increasingly successful, but also more complex and less interpretable. In the recent surveys, authors provide comprehensive reviews of techniques to integrate data-driven models with physics models. Most of them fall under one of the following categories: either a corrective source term approach, in which they explicitly address the problem of unknown physics, augmenting the PBM, describing the partial physics with DNN stuff. One added benefit of the Costa approach is that the physical laws can be used to keep a sanity check on the predictions. A similar approach has been used to model unresolved physics. They can enable coarse-scale simulations. You've got data assimilation, data-driven physics discovery. That can be used with the LiDAR data, the gearboxes, the infra stuff, okay? We've got the physics-informed neural network, which kind of takes the DDMs and it combines it with the whole physics-informed neural network. Reduced order modeling. Within the model order reduction approach, reduced order modeling is very popular, and all that. So there are many ways which we can combine the two. Industrial acceptance is definitely another key thing. Human-machine interface, using the 3D XR virtual reality, relevant use cases, and all that. That's all very much, what we need to do. So in conclusion, this paper is really just trying to, get the whole digital twin situation out there. It's proposing a set of ways to combine the data-driven and the physics-based models, and it says that this is what we can do to really bring about change in the wind energy sphere. So thank you if you made it so far. It's been a really long paper. I do encourage you to actually go check out the actual paper, which is in the description, but hopefully this gave you a pretty good idea. And yeah, always just drop something in the comments, like and subscribe if you enjoyed this